Why does the training procedure of a multilayer perceptron, or MLP, hold such significance? Well, it's the heart of the MLP's capacity to learn, process data, and execute tasks like classification, regression, or prediction with precision. Today we delve into this fascinating procedure, starting from topology design and data preparation to the actual training process, encompassing forward propagation, back propagation, and optimization. First on our list is the topology design. It involves two key elements: the number of layers and the activation function. An MLP is composed of an input layer, one or more hidden layers, and an output layer. The volume of these layers and the neurons within them directly influence the model's ability to comprehend complex patterns. The activation function, on the other hand, can be commonly observed as ReLU, or rectified linear unit, for hidden layers, and softmax or sigmoid for the output layer, which varies depending on the task at hand. Next, we move on to data preparation. This begins with collecting a representative data set for the problem you aim to solve. The data then goes through a pre-processing phase, which includes normalization or standardization for a smoother and more efficient training process. It might also involve handling missing values and encoding categorical variables. The data is then divided into training, validation, and test sets, each serving unique functions in the training process. Now, we move on to the actual training procedure. It begins with forward propagation, where the input features are fed into the network, computed through the hidden layers, and finally, the output layer produces the prediction. This prediction is then compared with the actual target values using a loss function to calculate the error. This error is then backpropagated to calculate the gradient of the loss function, which is used to adjust the weights in the direction that most reduces the error. To make this process more efficient, an optimization algorithm is used, such as stochastic gradient descent, ATOM, or RMSprop. Regularization techniques like L1 and L2, regularization or dropout, are applied to prevent overfitting. This process of forward propagation, backpropagation, and optimization is repeated for many epochs until the validation performance stops improving, indicating convergence. Lastly, the model is assessed using the test set to measure its performance on unseen data. The model's hyperparameters are adjusted as needed to improve performance. In conclusion, the training procedure of an MLP is a multi-step process that requires careful design, preparation, and iterative optimization. It underlies the MLP's ability to learn from data and perform tasks accurately, making it a cornerstone of many machine learning applications. So the next time you come across an MLP, remember the intricate process it has gone through to become the intelligent model it is.